Okay, so hello everyone. So let's see some problems from previous year gate exam and especially from metal cutting process. So let's see one by one. So the first question you can see here, a cuboidal part has to be accurately positioned. First, arresting. You can see here. So here we have these are four arrangements. Arresting 6 degrees of freedom and then clamped in a fixtures. Clamped in a fixtures. You can see here. To be used for machining, locating pins in the form of cylinders with hemispherical tips are to be placed on the fixtures for positioning. Four different configuration of locating pins are proposed as shown. Which one of the options given is correct? So you can see here we have four options, correct? This is option 1, 2, 3 and 4. So this question is related to 3 to 1 principle. And what do you mean by 3 to 1 principle? So simply it states that by using 3 pins we can restrict by using 3 plus 2 plus 1, that is 6. By using 6 pins we can restrict 9 degree of freedom. Correct? 9 degree of freedom. Is it right? How it can arrest 9 degree of freedom? So in a space, if I see, you can see here, if I draw a three-dimensional state of stress condition, three-dimensional. So this is, let's suppose this is X, this is Y, and this is Z. And in 3D space, if we have any object, three-dimensional object like this, so this object can translate along positive X direction and negative X direction. Is it clear? In this, we consider both positive and negative motions, correct? Motions in positive direction and negative direction. Is it right? So how many total translatory motions are there? So if I say, so here we have total translatory motion is equal to 6. Total 6 translatory motions are there, and similarly if I talk about rotatory motion, then here we have 6 rotatory motions. Is it right? 6 translatory motion and 6 rotatory motion. Correct? So with the help of with the help of these 6 pins, we can restrict 9 degree of freedom. Is it clear? We can restrict 9 degree of freedom. Is it right? And how we can restrict? So you can see with this example. So you can see in option 1, at the bottom surface, you can say this is a bottom surface. Is it right? This is a bottom surface. And at the bottom surface, we have 3 pins. So with the help of these 3 pins, let's suppose this is pin A, B and C, correct? So with the help of these 3 pins A, B, C, we can restrict how many motions? So this body cannot translate in the downward direction. So it can restrict one translatory motion. And how many rotatory motion? Obviously, this body cannot rotate about x-axis and z-axis. It only rotates about y-axis. So by including all the positive negative direction, correct? Here it can restrict 4 rotatory motion. So simply can I say with the help of these 3 pins, we can restrict 5 degree of freedom. And now let's see if we have another 2 pins, that is D and E, which is placed on this plane, correct? Which is placed on this plane, correct? So with the help of these 2 pins, we can restrict one translatory motion along the, if I say this is x-axis and this is z-axis and this is y-axis. So according to this axis system, this these 2 pins D and E can restrict one translatory motion along the positive x direction. And similarly, if I talk about rotatory motion, then it also prevents the rotation about y-axis in clockwise and anti-clockwise direction. Yes or no? And another pin you have, you can see this one in the third plane. And let's suppose this pin is nothing but this is F. So with the help of these F pin, it can restrict one translatory motion. So these are the motions which can be restricted by the pins. So how many total pins we use? 6. And similarly, how many motions can be restricted? So you can see here 3 translatory motion and 6 rotatory motion. So total 9 motions can be restricted by these 3 pins. Correct? And this option 1 is completely satisfied this 3 to 1 principle. So this one is right. And let's see another one. Let's see another one. Let's see another one. And once again, I'm writing here. This is A, this is B, and this is C, and this is D, and this is E, and this is F. And now you can see in this we have 4 pins. 4 pins. So here we have one extra pins. Correct? Here we have one extra pin. So this option is wrong. And similarly, you can see here in this at the bottom plane we have 3 pins, but on this plane we have only 1 pins. That's why this is also wrong, because at least 2 pins are required, otherwise it cannot completely restrict the rotatory motion. Yes or no? And similarly here we have so many pins. This one is extra pin, this one is sorry, and this one is also extra pin. So because of this option is also wrong. So according to this, if I see which option is right, configuration P1 arrests 6 degree of freedom, while configuration P2, P4 are P2 and P4. You can see in P2 we have extra pins, and in P4 we also have extra pin, and here we have less pins. Is that right? Here we have only 5 pins. So P2 and P4 are over constrained, while as configuration P3 is under constraint. Is it clear? So option A is a right answer. Let's see another option. Configuration P2 arrests 60 degree of freedom. This is wrong. Configuration P3 and P3 arrests 60 degree of freedom. This is also wrong. Configuration P4, and let me check. If configuration P2 arrests 60 degree of freedom, P2, configuration P2 arrests 60 degree of freedom, while configuration P1 and P3 are over constraint. So this is wrong. Configuration P2 and P4 are over constraint. Configuration P1 is under constraint. This is also wrong. And this is also wrong. So correct answer is option 1 only. Correct. So let's see another question. A drilling machine is to be designed to have a single spindle speed ranging from about 110 rpm. So this is drilling operation in which designed to have 6 spindle speed ranging from. So the number of speed is 6, ranging from means N1 is 110 rpm, and N6, the last speed is 650 rpm. Assuming a proper series of the layout of the speeds, determine the value of all those 6 spindle speeds, modify the computed value so as a render then acceptable as a standard. So as you know that it follows, if it follows GP, geometric progression, so for this the N2 can be written as some k times of N1. Correct? Similarly, N3 can be written as N2 times k times of N2, or simply you can say k square times of N1. So if I write N6, so can I say this is k to the power 5 times of N1, and N6 and N1 is given, so k can be written as N6 by N1 whole to the power 5. Sorry, 1 by 5, not 5. Correct? So from this you can say here, this is 650 over 110 whole to the power 1 by 5 means 0.2. So let me see, 650 over 110 and whole to the power 0.2. So it becomes 1.4266. This is K. So let's see. So N2 is, sorry, N1 is already given here. That is 1110 RPM. So what about N2? This is 1110 into 1.4266. So simply here we get 1.56.9, or instead of here I am writing 157 RPM. And what about N3? 157 into 1 point. So simply you can write 157 into 1.4266. So after multiplying this, here I am getting 223.97. So here I am taking as an integer, that is 224 RPM. So what about N4? So this is 224 into 1.4266. So after this, here I am getting 319.55. So here I am taking 320 RPM. So what about N5? So 320 into 1.426. 320 into 1.4266. I am using this formula only. Is it right? N2 is equal to K times of N1, N3 is equal to K times of N2, and similarly N4 is equal to K times of N3 similarly. So after calculating this, here I am getting 456.512. So let's see, here I am writing 457 RPM as an integer, and N6, which is already given here, that is 650 RPM. Is it clear? So if it follows geometric progression, so these six speeds are given like this, yes or no? Okay, so let's see another question. When milling a slot of 20 mm wide, 10 centimeter long in a rectangular plate of 10 centimeter by 20 centimeter, means we have a rectangular plate. Like this. So this is the workpiece. So this is 10 centimeter by 10 centimeter by 20 centimeter. This is object. Cutting conditions used. Cutting speed is given here, that is 60 meter. Cutting speed is 60 meter per minute. And the diameter of the end mill, which is 20 millimeter. And number of flute, means number of tooth, is 8. And the feed, this is already given here, that is 0.01 millimeter per flute per revolution actually. So this is feet per tooth. And the depth of cut is also given here, that is 3 millimeter. Find the cutting time for this operation. So we need to calculate machining time. Is that clear? So when milling a slot of 20 millimeter wide, 20 millimeter wide and 10 centimeter long, 20 millimeter wide and 10 centimeter long. So we need to cut this much amount of slot. Is it right? And this is no information regarding thickness. So let's, here I am assuming this much total material can we need to remove it in a one run of our milling cutter. Is it clear? So this is 20 millimeter, correct? So 20 millimeter wide and 10 centimeter long, a rectangular slot we need to cut. So the machining time to cut this slot is nothing but the length that can be traveled by the tool and the table feed. So table feed is nothing but this is feed per tooth into N into Z. So you can see Z is given but N is not given. So simply can I say the velocity is nothing but this is pi d N by 1000. So from this we can calculate n. So can I say n is nothing but 1000 p over pi d, and if I put these values here, 1000 into 60 meter per minute over pi into diameter is 20 millimeter. So after calculating this, here I am getting n. So let me see how much we get. So 6000 into 60 over pi over 20. Is it right? So this is 955.44414. So let's put this value in integer form, that is 956 rpm. So after getting this, the machining time can be written as L by ft into n into z. So let's see, this is 10 centimeters, so 10 into 10 in millimeter. Speed is already given here, that is 0.01 millimeter per flute, into n, that is speed 956. And what about number of teeth? So here we have 8. So after calculating this, we get this value in minutes. So let's see after calculation how much we get. So 100 over this. So this is 1.308 minute. So this is the right answer. So the key point for this question is, first you need to understand how much length we need to cut and how much speed we need to have in the milling cutter. Yes or no? A 6-speed gearbox. A 6-speed gearbox has to be designed for the headstock of central lathe for turning mild steel and cast iron rods of diameter ranging from 100 mm to 200. So number of speed is given here 6, and the diameter of the steel is 100 millimeter, and the diameter of cast iron is 200 millimeter. If the maximum and minimum cutting speed permissible as 120 meter per minute, the maximum is 120 meter per minute and the minimum speed is 40 meter per minute respectively, what should be the value of those 6 spindle speed? Is it right? So this is a conventional problem actually. So first, and here two materials are given here. You need to calculate all 6 speed. So let's see how we calculate this. So the diameter is given, maximum and minimum velocities are given here. Is it right? So what should be the values of those 6 spindle speed? 100 diameter ranging from 100 millimeter to 200 millimeter by carbide tool if the maximum and minimum cutting speed. Okay, a 6-speed gearbox has to be designed for a headstock of a center lathe for turning mild steel and cast iron rods of diameter. So this is not a diameter of steel. Actually, this is the range of diameter is given here. Correct? So this is minimum and this is maximum diameter. If the maximum and minimum cutting speed permissibles as 120 meter per minute and 40 meter per minute respectively, then what should be the values of those 6 spindle speed? So this is a very lengthy question actually. First you need to calculate. Let's suppose if here we have 4 combinations. You choose minimum diameter with minimum velocity and maximum velocity. So in both the cases we get different speed. So you need to calculate actually maximum speed and minimum speed. So let's see how we get. So as you know that, let's see, as you know that The velocity is nothing but this is pi d n by 1000. So first you need to calculate speed with 1000 v over pi d. Is it right? And now the question is, what is n max? When you get n max? N max can be get when the speed will be taken as maximum and the diameter will be taken as minimum. Is it right? So like this you can calculate. So from this the maximum speed is 100 in 120 over pi 3.14. So this is, this is not 100, this is 1000. Correct? So 120 into 10, that means 120 into 10 for pi. So here I am getting 382 rpm. And similarly we can also calculate, if I calculate n minimum, so minimum speed is nothing but this is 1000 into minimum velocity, that is 40, and the maximum diameter, that is 2. Correct? So 40 into 1000 and along with pi divided by 200 divided by 1/4. Here we get n minimum is nothing but this is 64 rpm. So here I am taking integer value. So let's say, suppose if I say n1 is nothing but this is 64 rpm, and the n6, that is maximum speed, is 300 rpm. Is it right? These diameters, these speeds are already given, and this is 6 spindle speed. So once again, can I say this is nothing but n6 is equal to, I already told you in the previous question, k to the power 5 into n1. So from this, k can be written as n6 by n1 whole to the power 1 by 5, and n6 is nothing but this is 382 over 64 over 0.2. So after getting this 382 over 64 whole to the power 2. So this is, the k is nothing but this is 1.4294. Yes or no? So simply if you write n2, so can I say this is k times of n1? So this is nothing but this is 1.414294 into n1, that is 64. So this is 91.48, or simply you can say 92 rpm. Is that clear? After simplifying this, here I am getting 92 rpm. And similarly, what about n3? Can I say this is k times of n2? And already we know that. So after putting this, here I am getting 132 rpm. Is it right? And similarly, you can also find out for n4 and n5. Is it clear? So I am not calculating because n1 is already given here, n6 is given, k is given here. After getting k, just find out n2, n3, n4, n5. Yes or no? So like this, you can solve this problem. Okay, so let's see another question. In a drilling operation, a twist drill of 30 mm diameter with point angle of 118. So the diameter of the drill bit, nothing but this is 30 millimeter, and point angle, that is 2 alpha, is also given here, that is 118 degree. In CNC milling, command is used to execute drilling operation. The command is given here G90 G01 Z. This is not given here. I need to calculate F20. The datum is defined on the top surface of the work material and the approach distance is 3 mm. Then to achieve a cylindrical hole depth 40 mm and the z coordinate is. So let's see, suppose if I draw a workpiece, it is looking like this and its thickness is 40 mm. Is that right? Its thickness is 40 mm. So this is our workpiece and here we have a tool positioned here like this, the position of tool. So this gap is already given here, that is, and obviously for complete cutting of this work material, you need to move this tool up to this. Correct? This much amount of minimum travel is required. The datum is defined on the top surface of the work material. So let's suppose if this is the datum. So in this question, the datum is defined on the top surface of the work material. Then you can see approach distance is 3 mm. This is approach which is equal to 3 mm. And this is also already given here. This is 40 mm. And this is datum. And you need to calculate this distance x. So if I draw a line perpendicular here, so this is half of the diameter. Let's suppose this is x. So what is x? So x is nothing but this is 3 by 2 cot alpha. Is it right? So diameter is given already here, that is 30 by 2 cot alpha is 118 divided by 2, that is 59 degree. So after simplifying this, the x is nothing but here I am getting 9.0129 millimeter. Is it right? So actually in this question, we need to calculate this length. Is that right? And this is the distance traveled by the tool. This z coordinate. So what is z coordinate? This is 40 plus x. 40 plus 9.0129. So z is nothing but this is 40.0129 meter. This is the answer. So the final code is, if you want to write final code, so this 90.01 Z 40.9 40 point, sorry, 49, not 40. 49.0129 F20. This is our final code. And this one is the answer. Is it right? So like this, you can calculate the answer. Okay, so let's see another question. A shaft of length 90 millimeter. A shaft of length 90 millimeter has a tapered portion of the length 55 millimeter. So you can see we have this question actually. This is a very simple question. Like this. Suppose we have a shaft like this. Length is given here. This length is also given here. So what actually given here is, see, a shaft of length 90 milli. So the total length is 9 here. Has a tapered portion of length 55. This length given here, that is, let's say small l, 5 millimeter. The diameter of taper is 80 millimeter at one end and 65 at other end. So here we have diameter 80 mm and here we have diameter 65 mm. Correct? If the taper is made by tailstock set over method, the taper angle and the set over distance is. So first here I am going to calculate taper angle. Taper angle is nothing but this is 2 alpha. So don't be confused with this. But here we have one relation. Tan alpha is d1 minus d2 by 2 times of small l. What is d1? This is 80 minus 65 but 2 into 5. After simplifying this, here we get alpha is equal to 7.765 degree. What is 2 alpha? Just multiply with 2, then it can be written as 15.53 degree. And if you convert this value in radian, then it can be written as and remember, in 1 degree, how many radians are there? 60 radians. Is it clear? So in 0.53, how much radian? So 0.53, this is nothing but 31.8. Simply it can be written as 15 degree 31 sorry, not this is minute, correct? 31 minute 1.8 minute, or simply you can say 32 minutes. So 15.32. So this one is the right answer, correct? And similarly you need to find out offset length. So offset length is nothing but it can be written as 1 minus 2 by 2 times of small l into capital L. Is it right? So this is nothing but this is 80 minus 65 over 2 over length, that is 55, to total length, that is 90 mm. So from this here I am getting 12.2 27 millimeter. So the correct answer is option A. So you just put all the values D1, D2, 12. You can see this is D1. Here I am writing D1 is 80 millimeter. D2 is 65 millimeter. Small length is 55 millimeter. And capital length is 50 millimeter. This is already given in the question. Correct? Okay, so let's see another question. A hole of 20 diameter is to be drilled in a steel block of 40 thickness. A hole of 20 diameter is to be drilled. So the diameter of the drill bit is 20 millimeter. Get right, 20 millimeter. To be drilled in a steel block of 40 thickness. Let's say if I say this is small length, thickness of the block is small length. Let's assume this is 40 millimeter. The drilling is performed at a rotational speed and is given, that is 400 revolution per minute. Speed is given here, that is 0.1 millimeter per revolution. The required approach and overrun of the drill together is equal to radius of the drill. This approach plus over travel is equal to the radius of the drill, that is 10 millimeter. The drilling time. So we need to calculate drilling time, or we can say machining time. So the machining time is nothing but this is capital L by Fn. And what is capital L? Small l plus approach plus over travel by Fn. So by putting all the values here, so this is 40 plus 10. This is A plus O is equal to 10 over feet, that is 0.1 into, that is 400. So after simplifying this, here I am getting machining time. So let me see, 50 over 0.1 over 500 by 400. So this is 1.25 minute. 1.25 minute. This is the right answer. This is the right answer. Okay, so let's see another question. A disc of 200 outer and 80 inner diameter is faced, means you have a disc whose outer diameter is 200 and inner diameter is 80 correct? Let's say this is capital D naught is 200 and di inner diameter, that is 8. And we need to turn along this direction, correct? And the feed is given here faced at, yeah, this is a facing operation, so faced at a feed of 0.1 millimeter per revolution. Means in every revolution the tool can enter into the seat by 0.1 millimeter. With a depth of cut is 1 millimeter. The facing operation is undertaken at a constant cutting speed. Velocity is given, that is 90 meter per minute. In a CNC lathe, the main tangential cutting force, that is FC, is also given here, that is 200 Newton. Assuming approach and over travel of the cutting tool to be 0, the machining time in minutes. So the machining time, you can see how much time is actually required. So you need to travel the tool up to this thickness only. Is that clear? So if I say the length is nothing but, can I say the length is nothing but this is 200 minus 80 by 2. So this is 200 minus 80 means this is 120 by 2, 60 millimeter. This much amount of length is traveled by the tool. Is that clear? So the 60 millimeter and feed is given, that is 0.1 millimeter per revolution, and we need n. So how we calculate n? So if I took average diameter, this is nothing but 200 plus 80 by 2. So this is 140 millimeter. So for this, the velocity can be written as speed is 1000 V over average cutting speed is given here 1000 V over pi d average. So if you put this value here, then we get 1000 into V, that is 90 meter per minute over pi into 140. After simplifying this, how much we get? Let's see. 20.4.73. So let's say I take this 0.05 RPM. So as you know that the machining time is nothing but L by Fn. So this is 205. So what about Tm? So let me see. 2.93. Get clear? From this we get, let me see, T over 20.5, 2.926, or simply you can say 2.93 minute. Is that clear? This is the answer. So the correct answer is option A. And neglecting the contribution of the feed force towards the cutting power, the specific cutting energy in joule per millimeter cube. So this is the continuation of previous question. So the, as you know that specific energy is nothing but that is cutting power over material removed rate. And what is cutting power? That is Fc into cutting velocity into MRR. And MRR is nothing but that is volume of the material removed over machining time. So machine time I already calculated. So let's see how much volume is removed. So in the previous operation, we have, you can see here, the cylindrical workpiece whose inner and outer diameter is given here. And in facing operation, this much amount of material can be removed. This is 1 millimeter. Is it clear? So the volume of material removed for this is nothing but this is pi by 4 E naught square minus di square into length, or you can say thickness. And the depth of cut is already given here, that is depth of cut is nothing but this is 1 millimeter. Is that right? So instead of thickness or length we take depth of cut. So pi by 4 into 200 square minus 80 square into 1. Let me check, the diameter is 200. Yes, 280. Let's see how much. 100 square minus 80 square. So from this here I am getting the total volume that can be removed is 26,396.16 millimeter cube. So you can see the specific energy consumption is, cutting force is already given here in the previous question. You can see that is 200 Newton and cutting velocity is 90 meter per minute. 200 into 90 meter. So can I say this will be converted into millimeter and also converted from meter minute to second by dividing 60, or simply here I am writing 60 into volume that can be removed is 2696.16 over machining time. Already here I am getting 2.93 minute. So 2.93 into 60. This 60 cancel out with this. After simplifying this, how much we get? Let's check. So after calculating this, here I am getting 2000 joule per millimeter cube. Sorry, this is Newton millimeter. Yes, not 2000 joule. 2000 Newton millimeter per second. So if I divide with 1000, then here we get 2 joule per millimeter cube. So don't make this mistake. So the correct answer is option B. Is it right? Because from this here I am getting Newton millimeter per second. Sorry, Newton millimeter per millimeter cube. Is it right? So first you need to convert this millimeter into meter, because Newton meter can be written as joule. So simply if you divide this value with 1000, then you will get this value in Newton meter, that is joule. Is it clear? That's why I am dividing this 1000. So don't make this mistake, correct? Okay, so let's see another question. In a single pass drilling operation, through a hole of 15 millimeter diameter is to be drilled in a steel plate 50 millimeter. In a single pass drilling operation, through a hole of 15 millimeter diameter, the diameter is 15 millimeter, drilled in a steel plate of thickness, so let's say small l, this is 50 millimeter. Drill spindle speed is 500 rpm, n is given, that is 500 revolution per minute. Speed is also given here, that is 0.2 millimeter per revolution, and drill point angle is 2 alpha is given here, 118 degree. Assuming 2 millimeter clearance at approach and exit, means approach is equal to 2 millimeter and over travel is 2 millimeter. The total drill time, so we need to calculate machining time. Is that clear? So you can see here, first you need to calculate total length only. So this is nothing but this is L plus X plus A plus O. Correct? So what about X? X is nothing but this is D by 2 cot alpha. So D is given, that is 50 by 2. Cot alpha is nothing but this is 59 degree. Let's suppose this from after calculating this here I am getting 4.5 millimeter. So what about total length? This is 50 plus 4.5 plus 2 plus 2. So this is length, total length traveled by the tool is 58.5 millimeter. Correct? So what is machining time? So machining time is nothing but this is L by Fn. L is already determined here. Speed is given here, that is 0.2, and N is at RPM. After simplifying this, 0.58 minute, and if you multiply with this, then we get second. Multiply with, then simply here I am getting PM is equal to 35.10 second. So the correct answer is option A. Exact value here I am getting. Okay, so let's see another question. During orthogonal machining of mild steel specimen with a cutting tool 0 rack angle, here alpha is given, that is 0 degree. The following data is given. Uncut chip thickness, that is T1 is given here 0.25 millimeter, and chip thickness, that is T2 is also given here, that is 0.75 millimeter. Width of cut B is given here, that is 2.5 millimeter. Normal force, that is FT, this is cutting force, not FT, 950 Newton. and thrust force, that is Ft, is also given 475 Newton. The shear angle and the shear force respectively. So here I need to calculate first shear force, shear angle. First we need to find out shear angle and the shear force. So as you know that tan phi is nothing but this is r cos alpha over 1 minus r sin alpha. And what is r? That is chip thickness ratio T1 by T2, which is 0.25 by 0.75. So this is 1 by 3. So from this, if I put these values here, 1 by 3 cos 0 over 1 minus 1 by 3 sin 0. Simply here we get 1 by 3. So from this, can I say the phi is nothing but this tan inverse by 3. This is 18.43 degree, 18.4349 degree. So this is shear angle. And similarly, if I need to calculate shear force, so can I say this is Fc cos phi minus Ft sin phi? Yes or no? And everything is given here, 950 cos 18.4394, sorry, 4349, or simply you can say phi minus 475 sin 18.435 degree. So after simplifying this, get 751.04 Newton.